The Set Theory Guide for Artists podcast. Didn't I warn you? This book has magical properties. She rents a Victorian dress and now she's moving across the country to live in an apartment in a Victorian house. And meanwhile, my special cape and my candle holder and my candle are in a box somewhere. No, I've got to wear this Chewbacca robe and I have this lighter. Well, anyway, the show must go on, as they say. Chapter 1, Part 2, continued. Hausdorff gaps, filters and ideals, and cofinality. Hausdorff gaps. After all this yard work, let's go inside and draw the curtains. Hausdorff gaps are gaps in omega to the omega, which is the set of functions f from omega to omega. That is the set of omega sequences of natural numbers. For example, here are two such functions. The first is the constant sequence 4, 4, 4, 4, 4, and the second is the sequence of even numbers 0, 2, 4, 6, and so on. If you had to say which is greater, is it f or is it g? We could say g is greater because eventually f of n is less than g of n. This is the partial order on omega sequences of natural numbers known as eventual domination. For f and g in omega to the omega, f is less than g if and only if f of n is less than g of n for all but finitely many n. Some such functions are incomparable. Below is an increasing sequence of functions in omega to the omega of length omega. And here is a decreasing sequence of functions in omega to the omega of length omega. The first element of the sequence is the function furthest to the right. Below are both families of functions together. Every function in the decreasing family eventually dominates every function in the increasing family. The question is, can we find h from omega to omega such that h fits between the increasing family of functions and the decreasing family of functions? How could we do it? In this example, both families of functions are intended to be size omega. If both families are size omega, then we can always find a function h between the increasing family and the decreasing family. That is, there are no omega-omega gaps in omega to the omega. An alpha-beta gap is two families, one an increasing family of size alpha, the other a decreasing family of size beta, where the increasing family is below the decreasing family, and where there is no h from omega to omega that fits between the families. Though there are no omega-omega gaps, if we increase the size of the families to omega sub 1, we can construct two families such that one can never find an h that fits between them. Hausdorff showed there are omega 1 gaps in omega to the omega, and we use that there are no omega-omega gaps. Filters and ideals. On each row below is the set of positive natural numbers, or think of any infinite set A, and the highlighted elements represent a subset. The collection of all finite subsets of an infinite set A is an ideal because the empty set, the collection of all finite subsets of A, because the empty set's in I. 2, if x and y are in I, then x union y is in I. 3, if x is in I and s is a subset of x, then s is in I. The empty set is a finite set. The union of two finite sets is a finite set. And a subset of a finite set is a finite set. An ideal on a set captures the sets that are small. The intersection of two small sets is small because it is a subset of both sets. Condition 2 says that you can't get into the big sets by taking the finite unions of small sets. The dual notion of an ideal is a filter. Represented below is the filter on an infinite set, which includes sets whose complement in A is finite, aka the cofinite subsets. The collection of all cofinite subsets in an infinite set A is a filter because A is an F. If X and Y is an F, then X intersect Y is an F. If X and Y is an F and X is a subset of Y, then Y is an element of F. An infinite set is a cofinite subset of itself. The intersection of any two cofinite subsets of an infinite set is also a cofinite set. And a superset of any cofinite set is a cofinite set. A filter on a set captures the sets that are big. The union of two big sets is big because it is a superset of either set. Condition 2 says that you can't fall into the small sets by taking a finite intersection of big sets. If I is an ideal on a set A, then F, the set of all X subset of A, X not in the ideal, is a filter on A. An ultrafilter U on a set A has the property that for every subset X of A, either X is in U or X is not in U. A filter F on a set A is principal if there's a non-empty subset E of A such that X subset of A, P is the set of all X subset of A such that E is a subset of X. We might wonder if there's a non-principal ultrafilter where condition 2 holds for infinite intersections. These kinds of questions will lead us to large cardinals. In the future, we will see filters defined on partial orders in the context of forcing. Cofinality. There was once an office located on the aleph sub omegath floor of a building. And every day, everyone took the regular way up, an aleph sub omega sequence of steps. Everyone loved the job, but the commute was a common complaint. Until one day when one worker made a ladder, an omega sequence of steps, a shortcut to the office. The ladder exists because aleph sub omega is the limit as n goes to omega of aleph sub n. Since there is an omega sequence of ordinals whose limit is aleph sub omega, the cofinality of aleph sub omega is omega. CF or cof of aleph sub omega is omega. If alpha is a limit ordinal, the cofinality of alpha is the least. If alpha is a limit ordinal, the cofinality of alpha is the least beta, such that there is a beta sequence which converges to alpha. An infinite cardinal kappa is regular if the cofinality of kappa is kappa. For example, omega is a regular cardinal. If a cardinal is not regular, it is singular. For example, aleph sub omega is singular. For offices on regular floors, there is no shortcut ladder. There is only the regular way. We saw in part 1 that an inaccessible cardinal shares key properties with omega. Being a regular cardinal is one of these properties. A cardinal kappa is weakly inaccessible if it is an uncountable regular limit cardinal. A cardinal kappa is inaccessible if it is an uncountable regular strong limit cardinal. A strong limit means that kappa is greater than the power set of any set below it. Workers on their way to the upper offices have a lot of time to think and start to ask themselves questions. How do we really know that we exist and all these offices exist? Do inaccessible cardinals exist? What does it really mean for an Ehrenstein tree to exist? What assumptions are made in the construction? What is a set? Is there a place where CH holds? Okay, what I would like to say for this is that I love Hausdorff gaps, and maybe I should have shown more about them, but maybe they'll come back, or maybe it's a different document or something. I just say overall I really liked this chapter, and I liked the colors and creating this color set that we can use so we can see. And that's all. So we'll see you next time.